In the previous lessons, we explored techniques to reduce the energy and environmental impact of applications, both from the infrastructure perspective and through conscious choices in software design and development. However, to verify the effectiveness of these techniques and to truly quantify the benefits achieved, it is essential to measure the energy impact of the applications. Without reliable data, any optimization strategy risks remaining abstract. While data centers, especially large-scale ones, are now able to monitor the energy consumption of various physical components with high precision, measuring the energy impact of a single application is a much more complex task. This complexity increases even further if you want to move from measuring the energy consumed to estimating the associated equivalent CO2 emissions. In this lesson, we will focus precisely on this topic: how to measure the energy consumption and the environmental emissions associated with software, and what tools exist to do so. Knowing and monitoring the energy impact of software is important for at least three main reasons. Operational efficiency. Measuring energy consumption helps to identify bottlenecks, waste, and inefficiencies in application behavior, which often also result in lower service quality and higher operational costs. Informed design. To develop more sustainable software, it is essential to have tools that allow you to assess over time the effectiveness of design choices and implemented optimizations. Transparency and communication. The availability of measurable data enables organizations to credibly report their commitment to digital sustainability to customers, partners, and investors. Unlike hardware consumption, the environmental impact of software is much more difficult to isolate. This is because it depends on a heterogeneous set of factors: the source code and architectural choices, the workload generated by users, the type of infrastructure in use, the geographical location of computing resources, and the energy mix of the electrical grid used in each place and at each moment. In many cases, the organization that develops or manages an application does not have direct access to this information, especially if the software is run on public clouds. Even when the hardware consumption is known, if multiple applications share the same resources, it is difficult to accurately attribute the consumption to each of them. This makes the direct measurement of software consumption virtually impossible, unless very specific tools and advanced estimates are used. To overcome these difficulties, tools and estimation models have been developed that are able to provide a sufficiently reliable picture of the software's energy impact. These tools vary in precision and granularity depending on the context. In on-premise environments where the infrastructure is under the direct control of the organization, it is possible to use hardware-level tools and operating systems to monitor actual consumption. In cloud environments where visibility into the infrastructure is limited, predictive models and estimation tools provided by the providers or by third parties are used to calculate consumption and emissions based on resource usage and the location of data centers. In on-premise environments, where there is direct control over the machines, it is possible to obtain fairly precise measurements thanks to hardware and software tools. The most accurate solution is to use watt meters connected directly to the power supply of the machines. There are tools that can be installed on servers or on individual racks to provide real-time data on electricity consumption. While these tools provide real and highly precise measurements, their presence is not standard, and they require physical access to the machines and a specific setup. An alternative is to use measurement tools at the operating system level. These tools do not require the use of external hardware and are commonly available on every server. However, the estimates are limited to specific components, such as the CPU and GPU, and therefore will only capture part of the consumption, although this is usually the most significant part in most cases. Finally, some tools allow for estimating energy consumption by working directly at the software level. Among these, Scapander and Kepler use hardware-level and operating system-level tools to estimate the energy consumption of a single process on a computer, but they can only be used in conjunction with specific technologies. Today, more and more companies are choosing to migrate to the cloud to manage their applications and digital infrastructures. But while this choice offers numerous advantages in terms of flexibility and scalability, it reduces visibility over aspects related to energy impact. To address this need, The main cloud providers, Google Cloud, Amazon Web Services, and Microsoft Azure have started offering dedicated tools for monitoring the CO2 emissions generated by the cloud services used. These tools make it possible to estimate the environmental impact associated with the use of cloud resources, with varying levels of detail and update frequency. Google Cloud has introduced the Carbon Footprint tool, which is available free of charge to all users. This tool shows how much CO2 is generated by the consumption of cloud resources in each project, service, and geographic region. The data is updated monthly and follows recognized standards. A key strength of this solution is the ability to easily export data to BigQuery, Google's analytics engine, for customized analysis and integration into company reports. AWS also offers a similar tool called the Customer Carbon Footprint tool. It is integrated into the cost management console and allows users to view the evolution of emissions related to the use of AWS servers. Unlike Google, the data is provided with a delay of about 3 months and is updated monthly. However, in recent updates, AWS has started to provide more granular data, such as the ability to distinguish emissions by region and by service. Additionally, the data can be exported in CSV and Parquet formats, which allows for good flexibility in processing. Microsoft Azure has taken an even more comprehensive approach in terms of tools and features. The main tool is carbon optimization, which allows you to monitor emissions at the resource or resource group level with a 12-month history. Additionally, Azure provides an emissions impact dashboard based on Power BI, which allows you to track emissions not only from Azure services, but also from other Microsoft services. In summary, no provider currently offers a real-time view at the level of individual software processes, while all of them allow for a fairly accurate estimate of emissions related to the use of cloud resources with a granularity that ranges from the project or service level down to the detail of individual resources. Accurately measuring the impact of software is still a challenge, especially in distributed environments like the cloud. Some aspects to consider are granularity. Many metrics are only available at the machine level, not for individual processes or services, and are aggregated over rather long time intervals. Change over time. The carbon intensity of energy varies depending on the time of day and the region, making measurements dynamic. How this dynamic nature is taken into account by the estimates provided by cloud providers is currently unclear. Evolving standards. Each cloud provider offers measurements that are collected and aggregated differently, and as of today, there is no standard that allows for a direct comparison. In summary, measuring the environmental energy impact of software is a key factor in assessing the effectiveness of optimization strategies and guiding informed choices in application development. Unlike infrastructure metrics, software consumption is difficult to isolate and requires specific tools and models, often based on indirect estimates. Although current technologies still have limitations in terms of accuracy and granularity, they provide a useful foundation for integrating sustainability into software development and management processes. Looking ahead, environmental monitoring will increasingly become an integral part of software quality metrics, on par with performance, reliability, and security.